Isomorphism and isomorphic are words that might seem intimidating, but they are derived from the Greek word equal. And so if you want to understand isomorphisms conceptually, think of these terms as ways to show that two structures are equal. Isomorphisms are the functions that show a connection between two structures in such a way that shows how the two structures are really equal. Now that begs the question, what does it mean for two structures to be equal? Don't they just have to be identical? Well, not quite. The word equal can be applied to many contexts and can relate to structures that might not appear to be equal at all. For example, take a look at these two graphs here. Now you might think that these two graphs are not isomorphic, but they are, and showing that requires an isomorphism or a connection between two structures that exploits how these two graphs convey the same information about vertices and corresponding edges. Take a look at how we can do this. What if I were to make these two purple and these two purple, and then these three red here, and these three red here. Now, if you can look at this carefully, you can tell that these vertices and edges from both graphs share the same property. In fact, we could give all 5 different colors. We can use maybe a different color for this purple vertex here. And then let's use a different color for this vertex here and here. And use one more different color. Oh no, we already did that color. Let's do light blue. There we go. For that one. And now you should be able to see that all the vertices on the graph on the left are connected to the same vertices on both graphs. And so this teal vertex here is connected to purple and blue, but it's also connected to purple and blue on the other graph. These two graphs are really conveying the same amount of information. They're the same structure. Before we jump into the concept of isomorphic graphs, let's just start with equal graphs. Remember, isomorphism means equal, but in a way that preserves structure, not necessarily that specifics of that structure are the same. Just because two graphs are isomorphic doesn't mean that the two graphs are actually equal to each other in every way. We should be careful about what it means for two graphs to be the same. Actually, given our definition, this is easy. Are the vertex sets equal? Are the edge sets equal? We know what it means for sets to be equal, and graphs are nothing but a pair of two special sorts of sets. All right, let's do an example together. Are the graphs below equal? The first graph, G1, has a vertex set A, B, C, and then the edge set, we have that A and B are connected and B and C are connected. And G2, same vertex set, A, B, and C, and A, C are connected and C, B are connected. So no, here the vertex sets of each graph are equal, which is a good start. And also both graphs have two edges, but in the first graph, we have edges A, B, and B, C, while in the second graph, we have edges A, C, and C, B. Now we do have that BC is the same as CB, so that's not the problem. The issue is that AB is with AB and AC, since the edge sets of the two graphs are not equal, as sets at least. The graphs are not equal as graphs. Even if two graphs are not equal, they might be basically the same though. So in this instance, the graphs might still be basically the same. The graphs in the previous example could be drawn like this. And let me see if I can get a black pen here. There we go. Here I'll draw A, B, C, and here I'll draw A, C, B. So graphs that are basically the same but perhaps not equal are called isomorphic. Intuitively, Graphs are isomorphic if they are basically the same, or better yet, if they are the same except for the names of the vertices. To make the concept of renaming vertices precise, we give this definition here. An isomorphism between two graphs G1 and G2 exists. It's a bijection function f from V1 to V2 between the vertices of the graphs, such that an edge is an edge in G1 if and only if, when you apply the function to those edges, you get there's an edge between the outputs of those two functions is an edge in G2. So two graphs are isomorphic if there is an isomorphism between them. In this case, we write G1 is equal to G2. Now, an isomorphism is simply a function which renames the vertices. It must be a bijection, so every vertex gets a new name. You can think of the isomorphism as a renaming itself. These newly named vertices must be connected by edges precisely when they were connected by edges with their old names. Sometimes we'll talk about a graph with a special name, like KN or the Peterson graph, or perhaps draw a graph without any labels. In this case, we're really referring to all graphs isomorphic to any copy of that particular graph. A collection of isomorphic graphs is often called an isomorphism class. Now let's check real quick up here. We have these two graphs that were not equal, but they are isomorphic, and the way we would do that is we would create a function f, and I'm going to use a different color for function f, it's going to be purple, which sends a to a, so f of a equals a. We'll send b to c, so f of b equals c, and c to b, f of c equals b. And so this is the function, this is the isomorphism between these two graphs, and we can show that for any, between the vertices of graphs G, in graphs G1, here let's look at A and B, we have that this edge right here is an edge in G1 if f of A, which is A, and f of B, which is C, AC, we have this edge here between A and C. So this is truly a renaming function. We're relabeling things and getting the same structure. And so that's the importance here with this definition. Anyways, thanks everyone, and I'll see you in the next lecture.